Alright, so this audio lecture is going to be focusing on metabolic acidosis. And so metabolic acidosis is going to be a reduction in pH due to an increased production of acids in our body and or decreased bicarbonate secretion. Alright, so the first topic that we're going to be talking about is metabolic acidosis. So metabolic acidosis is a decrease in pH because we're acidotic. Okay, this is going to occur because we get a buildup of hydrogen ions in the extracellular fluid or a loss of bicarbonate. Remember that hydrogen is an acidic, is an acid, and then bicarbonate is a base. And so we are going to see that the pH is less than 7.35, and the bicarbonate levels, if it's due to a bicarbonate decrease, is below 22 milliequivalents. Right? So now the problem is that we have a decrease in pH. Our base excess in this point would look like it would be a negative value, so it's going to be more than negative 2.5, and it is a deficiency of bases. Right? So now we are too acidic for our own good. So this is caused by really two different things, either a hydrogen accumulation or a bicarbonate deficit, meaning we don't have the bicarbonate to bind the excess hydrogen ions that are in the extracellular fluid. And so this bicarbonate deficit can occur within intestinal or renal losses. Intestinal losses can include diarrhea, right? So diarrhea, you remember that from anatomy and physiology, that the pancreatic juice contains a lot of bicarbonate to neutralize the stomach acid, and if we have diarrhea, we can secrete or excrete too much bicarbonate in our fecal matter. Now, the renal origins might be that we are not reabsorbing enough bicarbonate in our nephron tubule. Now, hydrogen excess, so hydrogen buildup, can be because of a couple different reasons. So, tissue hypoxia, which can result in lactic acid production. So, tissue hypoxia can be the result of shock. So shock is increased vasodilation, meaning the decrease in blood pressure, and so now our driving force to deliver tissues with oxygen is not going to be there. We could have ketoacidosis, meaning that you are relying too much on breakdown of fats, right? So producing ketone bodies in the process. I know it's really popular. It's really popular to go on the keto diet. So the keto diet is when you eat a lot of fats in your diet, and so you're shifting your energy production to fats rather than carbohydrates and proteins. Other people who are susceptible to developing ketoacidosis are diabetics. So diabetics can't store glucose, and so they start to rely more heavily on other energy sources like fats, right? And so they produce ketone bodies that can turn into an acid, and so they donate. That means they donate a hydrogen. Drugs and toxins can include aspirin. Can include aspirin or various other drugs, so like antifreeze, hyperalimentation, which is given a artificial feeding. So people who lack gastric ability to absorb nutrients can oftentimes be delivered nutrients via an IV, and so that can lead to a decrease in chloride. So an increase in chloride. So hyperchloremia. Antifreeze can cause it by producing oxalates. So oxalates, when they're broken down, can result in renal failure, and so this renal failure can result in inability to secrete hydrogen or reabsorb bicarbonate ions. Now, the last one is going to be renal retention, and so this one is going to be this is essentially renal failure. Okay, so now our kidneys are no longer really functioning that well. Glomerular filtration has decreased too substantially, and so now we're getting a buildup of hydrogen ions in the circulation, and we can't remove it. So the manifestation is due to compensatory mechanisms. So this occurs early in the acidotic event. So the lungs try to fix it very quickly. Okay? Their goal is to increase the pH because we're in acidotic condition. And so how would we increase the pH? Well, we're going to increase our breathing, increase ventilation, because we want to decrease our PCO2, which is contributing to the acid-base balance. Yeah. It can be due to dyspnea, so labored breathing, difficulty breathing, and so if you slow down your breathing, CO2 is going to be increasing. Okay. Okay. So in the kidneys are going to try to excrete more hydrogen. Okay, and they're going to try to decrease the amount of hydrogen in our blood. This increases urine acidity, and if you review the buffer systems that are talked about at the beginning of this section, which I did not touch on, okay, I'm leaving that up to you guys, we see that urine acidity can increase or decrease depending on the buffering level.
Now, it can affect other systems of the body, such as anorexia, nausea, vomiting, abdominal pain, right? And that would kind of make sense. Like you're not, you're probably not maintaining the proper environment of that environment, so it's not really too prone to eating at that point. Okay, we see decreased neuronal excitability, okay, because the ions are all kind of messed up. Now, in the cardiovascular system, this can have pretty large manifestations, right? So, one of the big problems is the decreased responsiveness to catecholamines. Okay? Now, recall that we make small changes in our cardiovascular system using these catecholamines by activating receptors. Okay? So they'll be kind of less responsive to it. So if norepinephrine stimulates some alpha adrenergic receptors normally, that would cause vasoconstriction. But the receptors are not responding to the norepinephrine release from the neurons. So what we have here is we get the peripheral circulatory system is not responding to stimulation, and so what we have is the opposite response of vasodilation. Okay, so that means that the skin might be warm underneath or kind of red. Okay, we'll have decreased contractility, right, for the cardiac tissue itself. Okay. And if you have decreased responsiveness to get into these catecholamines, that explains the decreased contractility. Right now, when it tells you your heart to beat, it's not beating as strongly. Okay. You could get rhythmic patterns occurring that can develop pretty quickly. Okay. And this condition kind of perpetuates metabolic acidosis from lactic acid production, because if cardiovascular function decreases, we're further going to reduce the amount of oxygen that is getting to that tissue. Then that forces that tissue to rely on anaerobic respiration for ATP production, right? And instead of all this ATP that it normally is going to produce, it's going to produce some more lactic acid, which make things more acidic. So we could have muscle and bone issues as well. We could get bone weakening because remember that our bones can be used to buffer these systems as well. Okay, so we had several different buffer systems, and so one of the good ones in the bone is the bone, and we're releasing calcium carbonate to kind of sequester some of these hydrogens. So if we release hydroxyapatite, which is calcium phosphate, okay, that is hydroxyapatite, then we increase, that is in response to an increase in serum pH, right? So that would result in bone weakening and probably bone pain, okay? And just similar to pretty much all these is we see changes in membrane potential stuff. So here we have muscle weakness, probably because the proteins are not functioning correctly around that pH, but the membrane potential is also altered. Okay. So we could have muscle and bone issues as well. We could get bone weakening because remember that our bones can be used to buffer these systems as well. Okay, so we had several different buffer systems, and so one of the good ones in the bone is the bone, and we're releasing calcium carbonate to kind of sequester some of these hydrogens. So if we release hydroxyapatite, which is calcium phosphate, okay, that is hydroxyapatite, then we increase. That is in response to an increase in serum pH, right? So that would result in bone weakening and probably bone pain. Okay, and just similar to pretty much all these is we see changes in membrane potential stuff. So here we have muscle weakness, probably because the proteins are not functioning correctly around that pH, but the membrane potential is also altered.
All right, so in diagnosing metabolic acidosis, we're going to run an arterial blood gas, and we're going to expect a fairly normal oxygen concentration. Well, oxygen is probably going to decrease because now hydrogen ions are sequestering those hemoglobin molecules, and we can't bind bind the hemoglobin. Now, the blood chemistry is really what's going to be telling us the disorder. And so the determination of the anion gap. And the anion gap is a test that tells us really the balance between cations and anions. And so it tells us about the unmeasured anions. So these unmeasured anions can be things like lactic acid, can be like keto acids. Okay, so sodium is our primary cation in the extracellular fluid. Okay, and then we have chloride and bicarbonate being our primary anions, at least as far as electrolytes go. So you see that chloride is really elevated. Bicarbonate is smaller, and so normally this anion gap is about 6 to 9 milliequivalents, and so this is a little excessive. So normally it sits in this range of, we'll say, 6 to 12 milliequivalents, and so that means that normally there are unmeasured anions making up this gap between, because remember that sodium and then cations and anions are balanced, and so if we get a disruption in this, we can develop acidosis. And so we could see that here, so in this condition, we get sodium making up 142 milliequivalents, and then we would subtract the anions. And so specifically, since we're measuring chloride and bicarbonate, when we run a blood analysis, we run it through a machine, it tells us the concentrations, then we can determine the anion gap. And so if the anion gap is increased, so we're seeing this decrease in bicarbonate right here, which is allowing the anion gap to increase, then we can see that that is likely due to increased organic acids like lactic acid or keto acids. On this case, we can see that disruptions in chloride balance in the electrolytes. So sodium is again going to make up 140 to 145 milliequivalents per liter. Okay. Notice here that chloride is going up, and so chloride is thus balancing out our bicarbonate, and so now our bicarbonate levels are still going down, chloride levels are going up, and the anion gap is staying level. So this would be an example of hyperchloremia causing this acidosis, because it's essentially disrupting bicarbonate presence. Determining the source of the acidosis is going to be just as important as determining acidosis, right? So, especially for the treatments. Now, we're also going to run a complete blood count at this time, and really we're going to be looking for erythrocyte concentration. All right, so treatment of metabolic acidosis. We're really going to try to treat the underlying cause, right, and restoring the arterial blood gas values. Another way to treat the underlying cause is to deliver insulin, right? So if we are diabetic, we want to increase glucose storage in cells so we can use that as a resource and decrease our reliance on really adipose tissue and fatty acids. In the case that we have a disruption in chloride balance, we want to restore that electrolyte back to its original condition. And so we would see that we can use this in the ketoacidosis, diabetic ketoacidosis, but we're probably going to use insulin as our primary method of treatment in that form. In the case that we see that in the diabetic ketoacidosis, the individual is likely going to be dehydrated as well, because now the glucose present in the urine is creating an increased solute drag for water. The other option is to deliver really bicarbonate in a form, and so generally you will deliver sodium bicarbonate. The problem with this then is you're also delivering sodium, and so that sodium concentration is also increasing. So that is the end of the metabolic acidosis lecture. Okay. Stay tuned for metabolic alkalosis and respiratory acidosis and alkalosis.